Hi guys, this is Miss Lamens. We're going to be filling out the note sheet that you received at the beginning of class, or really it's a packet. So this should be the first page. Yesterday we talked about Lewis dot structures, which focused on the electrons, or rather the valence electrons in molecules. Today we're going to be talking about those bonding electrons. So if we look at, for instance, this example of a Lewis dot structure, the electrons that are sandwiched between these atoms are called bonding electrons. And anything that's not sandwiched between electrons, so these are sandwiched between atoms, are called non-bonding electrons. So today we're focusing on the bonding electrons. And those are what form chemical bonds. So what are chemical bonds? These are attractive forces that hold two atoms together. Now the focus here should really be on the word attractive forces. In order for attraction to happen, we need to have ions. Okay, so we need ions for this. Remember the idea opposites attract? Well, it's all coming into play right here. Remember that cations, which are positive, you could remember by the T, looks like a plus or it's like a kitty cat. Yeah. And then they're positive. This happens when electrons are lost. Anions are negative. You can remember this by a negative ion, or that it looks kind of like onion, so it stinks. And those form when electrons are gained. So we're familiar with this idea of ions, but today we're going to be introducing something different. Polyatomic ions. So what are polyatomic ions? Well, polyatomic ions, we just look at the word, you can see that we've got the word poly. If you've ever taken a history class, we know that polytheism means multiple gods. So polyatomic really means multiple, and atomic being atoms, multiple atoms. Okay, so the definition of a polyatomic ion is a group of atoms that are charged. Okay, so these polyatomic ions, even though they have multiple atoms in them, they act as individual ions. Okay, remember you can pause the video whenever you need to catch up. And one thing that is really important about polyatomics, even though they're kind of packaged together and there's multiple atoms, we never, ever, and just so you know, whenever science uses the word never, we really mean never, change the subscript numbers in a polyatomic ion. We're going to talk about what that means in just a moment. Never, okay? So I would pause the video, make sure you can catch up. I'm going to go ahead and erase everything. All right, moving on down. Okay, so the charge of an ion is based on its number of valence electrons. How do we know how many valence electrons an atom has? Well, there are a few methods. We can use electron configuration. So for instance, if we were going to find out the number of valence electrons for carbon, we would know that the electron configuration is 1s2, 2s2, 2p2. The number of valence electrons is the total number of electrons from the highest energy level, which in this case is 2. And we would just add the number of electrons together to find out the number of electrons. 2 plus 2 equals 4 valence electrons. Okay, so carbon has 4 valence electrons. So that's your first one. Another way you could do it is by looking at the group number on the periodic table. This is our shortcut Shortcut. So what does that look like? Well, let me show you a picture of a periodic table. So if you guys don't know me, I love using this ptable.com. I think it's pretty awesome. I would recommend that you use it. So let's take a look at this beautiful periodic table. You can see that everything is labeled, right? We got 1, 2, 3, 4, etc. What I'd like you to do is take a moment to take your own periodic tables out, and I'd like you to renumber your main group elements. Now remember, our main group elements are these ones and all of these ones. Okay, so we're just going to be numbering these two groups, or really this whole group here, our main group elements. I'm going to number them 1, 2, nothing different here, but now I'm going to skip all the way to the other side here. This will become 3, 4, 5, 6, 7, and 8. We can use these numbers to tell us how many valence electrons are in an atom. So for instance, we were trying to figure out the number of valence electrons for carbon. We can see that carbon is in group 4, and therefore it should have 4 valence electrons. So let's take a look back at what we wrote down. Oh, sure enough, we found that carbon had 4 valence electrons, okay? So this group number only works for your main group elements. The transition metals are a different story. You'll find that, I'm going to just call them T metals, transition metals have varying degrees of valence electrons, okay? So they don't have a set pattern of valence electrons. All right, so how can we use the number of valence electrons to determine the charge? Okay, the key to the game here is that we want 8 valence electrons. We want 8. We also call this a full octet, okay? When we have a full octet, we're just like a noble gas. Right? For instance, 1s2, 2s2, 2p6. This is the electron configuration for neon. Neon has 8 valence electrons. So like I said, we want a full octet. So how can we use this to determine the charge of an atom? Well, in addition to wanting 8 valence electrons, you're going to pick the easiest way out. So, elements that have 3 valence electrons or less, they will lose those 3 electrons. Because that's easier than adding 5 electrons to get 8, okay? Elements that have 5 valence electrons or more, they are going to gain electrons, okay? Because that will give us 8. It's easier to add 3 valence electrons to 5 than to take away 5 valence electrons, okay? Remember, when we lose electrons, we are going to become an anion, or sorry, we are going to become a cation. And when we gain electrons, we become an anion.